Okay, when using electron beams, you have to be careful with small output fields. They can be tricky to get right, and you have to make sure you're using them correctly or have really good data tables. So the output goes down as the cutout shrinks, and then sometimes what happens is the output will go back up again. It gets really weird. Not sure exactly why that happens. So if you were to put this circle, so this diameter 3.8 diameter circle, and compare it to what should be the equivalent rectangle, the output should be less, but instead it goes up, and you can see this output of 0.951 is basically the same as like a 4x4 or 4x36, but not the 3x4. The lesson being here, outputs at smaller field sizes compared to the energy is difficult. And for small fields, the profile can change dramatically. So here's some more output measurements with our dedicated circles. We have a bunch of circle cutouts in my department. This is profile for 3, 3.5, and 4 centimeter cutouts. And what you can see here is that this beam goes for not very flat, not very wide here, and as you get up to 4, it does start to have like a pretty dedicated flat uniform area right in the middle. Whereas here it's much more cone shape, and the area that it's flat is getting smaller and smaller. And so, we have these dedicated circle applicators or cutouts so that our physicians can look at this and see what they're actually treating at fuller field sizes. And one rule of thumb, we love this rule of thumb, energy divided by 2 is critical. So you can say, if you're wondering, like, is this cutout too small for this beam energy? Take the energy divided by 2, and if that's the diameter of the size of the cutout, it's getting on the edge of being too small. So here, for a 6 MeV beam, 6 MeV divided by 3, or divided by 2 MeV per centimeter is 3. So a 3 centimeter diameter cutout is a little small for a 6 MeV. And when in doubt, just measure the output. Physics should just measure it. Another thing that happens as field sizes get smaller is Dmax shift towards the surface. So here on 3 versus 3.5 versus 4, you can see this Dmax is slowly getting deeper. The Dmax of this beam is 1.5. It's a 6 MeV beam, and you can see it's starting shifter closer and closer to the surface. And you can see the cutout's getting smaller and smaller. It's going to pull that Dmax closer and closer. Another thing in this beam is you can see that entry dose increased a little bit, right? So here entry dose for the 4 centimeter output is below 80%, and then when you get up to 3 centimeter output, it's right at 80%. Not a huge amount, but it's something that does happen. You'll see all the time, physicians will want to treat some tiny little thing with some tiny little cutout in the 6 MeV cone, and we have to tell them, like, you basically can't do that. You have to add some margin to that if you want to treat with the electron. So here's a use for surface applicators. So as the size of the cutout that you want to use gets smaller, and the beam energy, I'll say, can't support that, you can use one of these surface applicators for small fields and low energies. So in this diagram we have, let's say, a 6 MeV electron beam with a 3x3 cutout. Here's a bunch of electrons coming down. These black lines are supposed to indicate the 3x3 electron field. And here's the depth dose that you get out of it. And you'll be treating maybe prescription dose as this red one, and you'll get the elephant foot shaped dose distribution out of it. But one thing you can do is, if you create like a lead applicator that goes on the patient surface, so instead of you'll have a lead cutout that goes right down onto the patient's surface. Above that you'll have like the machine applicator cutout, which is kind of flashing around the edge of this lead output, so that this electron beam is coming down right onto the patient's surface. So it's the same electron beam, just being collimated down here, and then you'll get a much better dose distribution right at the surface of the patient. You'll get a sharper penumbra, improved isodose lines and surfaces, and things like that. Every department should have outputs, tables, and data books used. Here's an example of ours. You can see we have for every cone, 6, 10, 15, 20, 25 cone, and every energy, 6, 9, 12, 16, and 20. And we fill out these enormous data tables. It takes a very long time to measure all these. These data tables are vast and can be used for hand calculations for each cone, each energy, several different source to surface distances, like usually we say 100 or 105 or 110, things like this. And these data tables, like this is like physics gets grumpy. I don't know if you notice physicists get grumpy or maybe dosimetrists get grumpy when you put a small cutout in a big cone. And the reason why is because we don't want to measure a 5 by 5 field in the 25 cone. If you want to use 5 by 5, just use the 6 cone because that's where we measured it. In fact, I have it in my data table here. There's a 5 by 5 in the 10 cone. Probably shouldn't. That should be in the 6 cone. Like if I had to support every single field size in every single cone, that would be measuring a whole bunch of data that I probably don't really need to. So I always say, put the cutout in the cone that best fits it, like the smallest cone that it will reasonably fit in, and just put it in there. Don't put a 10 by 10 cutout in a 25 by 25 cone. That should go in the 10 by 10 or the 15 by 15. And as always, use Monte Carlo to do all your measurements. So here's another audience participation question. Why do we have 5 different cones? Like in this day and age, maybe a long time ago when we were treating more electrons, it was obvious. Why do we have 5 different cones, right? This is from my variant Linux. I have a 6, a 10, a 15, a 20, and a 25, right? And I already said on the previous slide, use the smallest cone that will fit in the cutout. And so I think part of the answer is that 6 cone, pretty obvious. If you're treating something on the skin surface, you want to treat a small lesion, 6 cone usually fits that. The 10 cone used to be used extensively for post or lateral off-cord boosts for head and neck cancer. The 10 cone was the only thing that would fit between the patient's shoulder and getting that cone right up against their neck for like 100 SSD setup. 15 is kind of the bread and butter cone. We can use this every day. The 20 cone, this is used for a lot of chest wall boosts and things like that. You probably could accommodate them in the 25 cone. So these days with like the reduced amount of electron treatments, I think maybe we could get rid of the 10 cone and the 20 cone and treat everything else just between the 6 to 15 and the 20, right? And the 25 is the largest cone that will reasonably accommodate our electron beams. I don't think if we made a cone that was bigger than 25, that beam would be as flat as it could be over the course of the patient. And so that is that.